Good morning, everyone. I'm Chuanxin Lan, an engineer from Institute of Computing Technology, Chinese Academy of Sciences, and I want to introduce you AIBench Inference. Considering the diversity of AI models, AI frameworks, and data types, we search the state-of-the-art workers and extract several trained models which can represent the diversity. Although the workloads are comprehensive, the inference time is much shorter than other processing time. Therefore, the benchmark cost is affordable based on those comprehensive workloads behaviors. We propose a new workload characterization methodology, WPC, and propose a set of algorithms, systems, and architecture. In addition, we propose three representative inference models. This is our outline. AIBench inference workloads also cover many different networks, like CNN, ResNet, LSTM, and others. It also contains workloads for different data types, including text, image, audio, video, and 3D data. There are 19 representative AI tasks selected from 3 internet sources, which are search engine, social network, and e-commerce. And their models, dataset, and the size of the state-of-the-art model are displayed in this table. Next, we will introduce benchmark affordability. We test 14 tasks on V100, and from this table, we can find in high accuracy promise the inference time is short from system, so it is affordable to test mirror tasks. Then I will introduce workload characterization. We first introduce the traditional methodology. Cloud Suite performed a Microarchitecture-independent workload characterization of scale-out workload, and they concluded having a higher fronted scale is the inherent characterization that places the scale-out workloads into the distant workload class from desktop, parallel, and traditional server workloads. Using Microarchitecture-independent workload characterization, host analyzed 119 benchmarks from 6 benchmark suites. Spec CPU, 200, MediaBench, MiBench, Ball Informatics, Ball Metrics workload, and ComBench. The diagrams representing the NAT key Microarchitecture-independent characteristic of the 119 benchmarks. The darkest area represents inherent behavior patterns. Boxes represent clusters, and asterisks included cluster representatives. So performed RSA-independent workload characterization from various important intrinsic program characteristics relating to computation memory and control flow. The analysis is performed using a JIT compiler that emits RSA-independent instructions. The figure is the comparison of 5 RSA-independent metrics across spec benchmark, ordered by the area of the plugin. The lower right plot provides the result. The smaller values indented more regularity in the matrix. Our experiments found that all these three kinds of methodology have limitations for modern scale-out workloads. For Microarchitecture-independent and Microarchitecture-dependent method, we performed the experiments on a scale-out workload with C, Java, Python, Hadoop, TensorFlow, MPI implementations, and transitional workload with a C implementation. We found that having a higher front-end store is not the inherent characteristic of the scale-out workloads. For the RSA-independent method, we found that the introduction characterization similarly between two workloads implementations at the IR level does not guarantee their introduction behavior. Characterization will be similar at the other two levels. In order to achieve the diversity of workload behaviors, AIBench Inference adopts a new method characterization methodology named Word Picture Workload Characterization Methodology. WPC solves the limitation we discussed above. We present a word picture workload characterization inside the WPC methodology and the tool. WPC integrates Microarchitecture-dependent, Microarchitecture-independent, and RSA-independent characterization methodologies. It performs a whole picture analysis on hierarchical profile data across intermediate representation IR, RSA, and Microarchitecture to sum up the inherent workload characteristics and understand the reason behind the numbers. We collect the IR stream with the LLVM tool, feed them to a logical procedural model with no cache, and a pipeline model. We collect the binary stream with the pin tool, feed them to a perfect procedural model with no pipeline model but a perfect cache model, which always compiles all memory references in a single column. We use a performance maintenance unit talk like perform to obtain Microarchitecture metrics on specific processor. The IR level analysis is behind the runtime environment, and the OS and RSA independent, where the RSA level analysis is behind the OS and Microarchitecture independent. The Microarchitecture level analysis is fed by the OS and Microarchitecture independent. We conduct WPC on sort with C, Java, Python, Hadoop, TensorFlow, MPI implementations, and max multiplication with a C implementation. Sort and max multiplication represent a typical scale-out and transitional workload. Respectively, we have the following observations. First, at the Microarchitecture level, we observe that source different implementations lead to varied PKI, and the implementations using a high productivity language like Java, Python, or the framework with a high productivity language like Hadoop, TensorFlow have a higher front-end store that our more you see the transitional workload. Second, the RSA level will keep consistent trace with that of the Microarchitecture level. Third, each sort implementation's instruction interplay is similar at the IR level, and the gap is not more than 1.5 times The closed instruction interpret implies that each sort implementation's instruction locality is similar when including the effect of the runtime evaluation and the OS. This inconsistently at the IR level with respect to the other two levels, perhaps used to investigate what makes a difference. We speculate it is a static optimization that makes a difference. We try training of Java and Python's JIT completion operation and change to an interpreter model at the Microarchitecture level. The short Java and short Python's LE MPKI is reduced from 0.19 to 0.019 from 0.99 to 0.01 short Python JIT with short Python. The change LE-MPKI is close to that of short C and short MPI, but the performance of short Java and short Python data rate 6.4 and 2.2 times when training of JIT respectively. When training of JIT, the numbers of the RSA level also change, including short Hadoop. These wells further confirm the intent of JIT for the catch message. Putting pairs together, we conclude that having a higher front-end store is not the inherent characteristic of the scale-out workload. We measure the instruction max of all C and Java implementations workload multiple SHA-256 and sort at 3 levels, and compare their pairwise. Similarly, we have the following observation. First, the instruction characteristic similarly between two workload applications. Only the RSA and Microarchitecture levels do not guarantee their instruction behavior characteristics. We will be definitely similar. For example, Motor Java and Short C have high similarity at both RSA and Microarchitecture levels, and their constant distance are not more than 0.14. But there is low similarity at the IR level, with the constant distance being high at 0.26. Metro Java and Short C have different algorithms and runtime, and their instruction max reduce are agreed at RSA and Microarchitecture levels using the traditional RSA-dependent or Microarchitecture-dependent workload characterization. They would be considered similar. Second, the similarity of instruction characterizations between two workloads at the IR level is not necessarily consistent with those at the other two levels. For example, SHA-256 C and Metro C are similar at the IR level, but not similar at the RSA and Microarchitecture levels. Indeed, there are different. Micro C has lots of floating point operation, where SHA-256C is integer operation intensive. Third, implementations of the similar workload calling a dynamic library or distantly implementing The functions in the source code have significantly different workload characterizations at the IR level. For example, there are two C-long-range implementations of SHA-256, SHA-256, SSLC, and SHA-256C and SHA-256 SLC cross an open SSL dynamic link library, where SHA-256C directly implements SSL in the source code. We note SHA-256C and SHA-C are similar as their cost distance are less than 0.1 at 3 levels. In fact, SHA-256 and SHA algorithmically are similarly in instruction max as they both have intensive data costs and integrate operators. However, we observe SHA-256 SSLC and SHA-C are not similar at the IR level, but similar at the Microarchitecture level. The reason is that IR only produces an intertry to a function called the dynamic link library. As the previous benchmark subsetting work that aims to remove redundant workloads collect metrics at only one level, we calculate AI inference workload based on WPC across intermediate representation RSA and Microarchitecture. Finally, the inference model. We have three inference models: server model, serverless model, offline model, and the server model is the online server model. Quite proceeding capturing of an inference benchmark. The matrix is latency and time latency. The serverless model is loading machine resource on damage. The metric is the server start time, memory consuming, path throughput. Finally, the offline model is based on processing a base inference process of an interface benchmark. The metric is interface time and interface quality. The conclusion: the AIBench Inference is AIBench Inference website is that it continues 19 respective AI tasks and models, and have a WPC method, and have 3 models.